Welcome to Haltech Elite NSP Training Part 34. In this training tutorial, we're going to explore using our closed-loop fuel correction in our airflow or fuel model tuning within our Haltech Elites. Without further wait, let's jump in so we can check this out. Okay, so let's get started. We're going to be taking a look at working with our closed-loop fuel correction in order to dial in our airflow or fuel tables, whatever type of strategy we're going after here using our NSP software with our Haltech Elite. It is going to literally tell us how much we need to update our table by, and we can use it as essentially a template or a guide in order to sort things out. So let's just quickly recap here what's going on with the closed loop correction, what's going on with the tables we have to pay attention to, and then we'll turn our attention into actually calibrating and tuning. I'll run through an example here of a data log file and a paired calibration and just show you what I look for when I'm interpreting the data and being able to go in and actually edit the table based on what I'm getting out of my short-term fuel trim correction. So just to quickly recap what we've covered in some other training tutorials. When we're dealing with our closed loop fuel correction, we're going to find that we specify our target lambda or target air fuel coming from our lambda tuning or target air fuel area table here. This is going to be relative to the application we're dealing with, meaning the table will be scaled in RPM relative to the engine operation we're going to be running, as well as the input to the table is, in this case, I've changed this to fuel load. This is referencing map pressure, which is what my main fuel table here is based on. And I've scaled the table out here so that it's going to be going and referencing into boost pressure, also into all of this vacuum operation. This is going to allow me to specify what I want my target fuel to be at. And in this case of my speed density, volumetric efficiency based strategy, it is part of my fuel and airflow model because fuel mass is equal to air mass divided by target air fuel. That's our equation that we have to work within. We'll find that the target air fuel is coming from our target air fuel values in this table here. So if we jump back into fuel tuning here, we specify our target air fuel at whatever RPM and load input that we have in that table where the engine's operating at. That's going to be the starting point for the closed loop correction. We have to have a wideband that we've wired in or tied into our Haltech. That can either be an analog wideband or a CAN-based wideband. We've covered what that means in other tutorials, how to set up the wideband, how to configure it, make sure it's correct in the CAN-based and in analog voltage type of inputs. So we have our wideband tied in here. I'm using an AM-X series wideband tied into my Haltech Elite box here, my 2500 box. So we essentially now have everything we need in order for the closed loop operation to start to function. So we have to have our target lambda specified. We have to have our wideband reading accurately represented right here. And the Haltech's going to take a look at the target air fuel and the actual air fuel. And it's going to do a comparison between these and calculate what's known as our lambda or air fuel error. The error is the difference or the deviation between these two readings. That error percentage in the closed loop correction is going to be what drives the short-term fuel trim to make its adjustments. Now we have a proportional, integral, and derivative gain function, which we can find here under lambda tuning. These drive the response of the individual terms of our closed loop correction. So the proportional is looking at that lambda error in the instantaneous difference. We can find that's reported right here. There's our proportional contribution. The integral is taking a look at that error over a period of time. So how far things are off over time. We can see this is the contribution in percentage of adjustment in our short term based on the integral compensation. And we do have a derivative gain that's not typically used, and I have the table not even populated in here because I don't use it very often or if at all in most cases. The derivative is going to be taking a look at the rate of change over time in that lambda error. We can successfully implement the closed loop correction with just a proportional and integral type of gain factors here. And these values right now are just set to these generic values all of 1.0. This will arm the short-term correction to get it to start working, but it's definitely not going to be ideal. You want to speed things up a bit so that that closed loop control is going to respond a little bit quicker. Now, we have to also configure some settings in our wideband configuration in terms of the closed loop operation here. If we go to main, navigation tree, and we jump under fuel tuning, under O2 control, we have our parameters here that we need to go and assign and work with. In this case, I'm saying I'm allowing 25% adding or subtracting in that short-term adjustment. The short-term adjustment is going to be changing my base fuel injector pulse width. It's going to be either increasing or decreasing to try to reduce the lambda error. Zero lambda error means that I'm hitting the actual target air fuel to the actual. They're matching each other. And a deviation, either positive or negative, means that we have a fluctuation or deviation from actual to target. So we're allowing this much correction range to our injector. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.